Hello and welcome back for another little Max for Live tutorial. Today we're going to have a look at trance gates, which are basically audio gates or triggered audio envelopes, and they are controlled by some kind of step sequencer user interface usually. Someone wished for that as the topic of my next tutorial video, and I found it was actually a pretty good idea. So here we are, and let's get started. As always, when we do an audio effect, we start with plug-in and plug-out objects. And then we create two multipliers, which we are connecting to the plugin object, because this is the point where our envelope will later be inserted. Then we do our dry-wet mixing by creating 4 multiplier objects, one for the wet chain and one for the dry chain, which will then be added with these two plus operators right there. And then we connect them to the plug out. Connect these to the left inlets and this to the right inlets and this to our dry input right here. Then we create a signal operator. We can give it a starting value of 1. And then we create a reverse subtract by 1, which then will be connected to our signal operator. Let's drag this up here. Then we connect our signal operator to our wet chain and the reverse subtract operator to our dry chain. Now we create a live.numBox object or any other user interface object you want to use. Give it the prototype of a mount, and this is basically our dry-wet mixing. So now we're going to create our envelope, and we use the live.adsr object for that, which will be connected to these multipliers I mentioned earlier. Let's move that a little bit down, because now we need a little bit more space for user interface objects. And to make it more visually, I use the live.adsr UI object. And I connect it to the corresponding inputs of the live.adsr. You don't have to use this. You can actually directly connect live.dials or whatever you want to use to the live ADSR. But I always like to see my envelope curve, so I find that to be very useful. So now let's create some live.dial objects and use the time prototype for that and connect it to the inlets of the live.adsr UI object. We need 3 times a time dial for attack, decay, and release. And then we're gonna take the amount prototype and connect this, the right outlet actually, and use this for the sustain, because this one is scaled from 0 to 1. And then we use another live.numBox object for our slopes. We have to multiply this by 0.01. And let's change the range from -100 to 100. Connect it to the corresponding inlet and outlets. And now we duplicate this 2 times. 1 attack slope, 1 decay slope, and 1 release slope. Cool. So now we're moving all this a little bit closer together, because we actually need some more space for further patching. And now we can start to create our time-based stuff, so basically our step sequencer, which then will trigger our live ADSR object right here. So let's start to declare some timing stuff, and we use a live.menu for that this time. And let's give it some synced values like 1/8, 1/8 triplets, 1/16, also this as triplets. 132. 132 as triplets, and 164 should also be cool. Great, now give it an initial value of 0. And now we create a selector object and fill in the values from 1 to 5. Let's check that. That are actually 7 values. So we actually need the values from 0 to 6. That's how we do that. And now we create some messages to get the right format for our further objects. So we type in 8n, 8nt for triplets, 16n for our 16th nodes. And let's do that further on. Add the t for triplets. The same for our 32th nodes. The t for triplets at the end again. And then, last but not least, the 64th nodes. Actually, this outlet. And then we can use the translate object and translate node values to ticks. Ticks are actually time-based values which we pretty often use for synced sequencing. Then we prepare for our phaser object and append the ticks message. And then we create our first phaser object. And give it the attribute log1. So this phaser is always synced to our playback in Ableton. And this will be our master phaser. So this should have the length of our whole sequence with all these steps. So for this, we now gonna create a live.numbox object again with the amount of steps we want to use. Let's change the units to integers and give the range from 0 to 32. That should be enough. Here also to integers. 0 is wrong. Actually, 2 is a good starting point. Let's start with like 16. Now our phaser has actually the length of 1/8, but this should actually be the length of just one of our steps in our sequence. So now we create a multiplier. So our master phaser is equal to the length of one step times our step amount. And by doing it like this, we actually get a little problem with triggering the right order. So we need a trigger bang integer. Insert it right there. Connect the integer outlet to our right inlet and move this to our left inlet of our multiplicator. So whenever one of these values will be changed, it is triggered all the right way. Since our master phaser now has the length of our whole sequence, we need to subdivide it by the amount of steps again. So we use the subdiv object and connect it to our step count right there. So now our master phaser is subdivided into 16 equal subphasers, which we're going to use to further trigger our envelopes. Since our phaser is synced to Ableton's playback, we now have a little problem, because when the playback stops, our phaser and our sequence will now also stop. So now we need to create a second phaser, which will overtake its job when Ableton's playback isn't running. So we create another phaser without the log argument, and then translate the ticks into hertz. So we have our free running phaser with the same tempo. And then we create a selector object, so we can choose between both of these phasers. Let's drag that a little bit down. And now we connect our synced phaser to the third inlet of the selector object. And now we need to write something which decides when we use which of these phasers. So we create a change object right there. And then an isn't equal to 0 operator. And connect this to the change object. So when our phaser stops, it will output a 0. And if the playback is running, it will output a 1. Then we add a +1 there. And so it automatically switches between our synced and our unsynced phaser whenever the playback stops or restarts. And we also want to phase align both of these phasers, because we don't want any glitches or stutters when we change over to the free running phaser. So we create a is equal to -1 object and connect it to the change object. So now when our synced phaser resets its cycle, it will put out a trigger, which then goes to this sample and hold object right here, which we connect to our unsynced phaser. And then we create another reverse subtract from 1 object and connect it there. And then we create a plus operator and connect it to our free running phaser and the other inlet to our sampled phase value right there. And then we just create a modulo operator with the attribute 1. And now connect it to our selector object into the second inlet. Delete this. And now both of our phasers are perfectly phase aligned when switched from one to the other. A little feature most sequencers should have is some kind of swing option. And this we will also implement here. So we create a swing object, connect it to our subdivide object. And this one will divide our phasers from the subdivide object into 2 subphasers, which we can vary in length. So we can have a longer and a shorter phaser, depending on the swing value which we apply. But since we now doubled the value of our phasers we created, so they are twice as fast as we calculated, we also need to multiply our master phaser by 2 to compensate for the added speed. That's why we add a ×2 multiplier right there at the chain before it's reaching the phaser objects. The next part is a little bit mathematical in terms of counting logic and stuff, but I try my best to explain it as clear as possible. Now we create a plus operator and connect both inlets to the first and the second outlet of the swing object. The first outlet gives us the range from 0 to 1, and the second outlet gives us the number of which of both of the swing phasers is playing, so the first phaser and second phaser. By adding both of these, we are basically counting from 0 up to 2. Now we create another plus operator to add the second outlet of our subdivide object, which is giving us the number of our subdivided phasers. And this one we multiply by 2. So we're basically counting 0, 2, 4, 6, and so on. By now adding both of these counting algorithms, we have a counter which goes from 0 to our step value times 2. And it also applies, of course, different counting times for our different swing values. That was the whole point of doing it like this. But it actually counts too far because it counts twice as much steps as we have in our sequence. So we create a modulo operator to compensate for this and connect it to our step value. So we now basically just count 2 times for our sequence, but our values are all correct and we don't exceed our maximum value of steps. Now we apply a swing message to actually set our swing value. This goes from 15 to 85%, I think. So we connect this outlet to our swing message and change the value of our live.numbox right here from 15 to 85 and set the initial value to 50 because this is basically the centered value, so both phasers are equally long. And now we need to rescale our input right here. So we multiply by 0.7 and add 0.15. So now our value input is correct. Since we now finished all our timing stuff, we can now switch over to our user interface. So we create a live.grid object, which we will use for our step sequencing part. And we now need to modify it here and there. So we don't need those markers and we don't need our direction panels. And the most important thing is to set it to matrix mode. And then we just need one row and a flexible number of columns. So now we can just turn on or turn off each of those steps. Like this. And now we create a columns message. So we can dynamically set it with our step input. And now we're going to create a buffer object where all of our step values will be stored later on and from where we will read back all of the step values later. So we create a buffer and give it the name sec for the sequence and a size of 32 samples. One for each of our possible steps. We chose the matrix mode because by filling in our sequence, it gives us all the steps which are turned on, so the step number and a 1 for turned on. And this is pretty cool for filling our buffer object. So we create a trigger object with the list and a clear message. The clear message will be connected to our buffer, and because it just gives us the information of the steps which are turned on and not if something is turned off or something like that, we need to clear our buffer every time the sequence changes. Then we create a zl.iter2 object, which gives us the list in value pairs. So the number of the step and a 1. Then we unpack those and create a peak object to write these values in our sec buffer, where the second inlet is the value for the step and the first is the position. And because our buffer counts from 0 and not from 1, we have to insert a -1 operator right there. And as you can see, our buffer is now filled with the data values from our live.grid object. Now, to actually visualize what is happening in our sequence, we create a snapshot object. And we want to snapshot the value every 30 milliseconds. And because we only need integer values for that, we add an integer object in between. And then we also need to add a +1 because our live.grid object counts from 1 and not from 0, as mentioned before. And then we connect it there and initialize a time value. And it's not running because, let me think. I also need to initialize the step value, of course. And now, as you can see, it works perfectly fine. And also, when we change the step number, everything runs as expected. And now we're heading to the last part of this device by building our triggering logic. So we're creating a round object with the value 1. So we round to integer values and give it the nearest 0 attribute. So we just want to convert our values to integers but not actually round them. Then we create a change object. And then we also create a isn't equal to 0 object. And when we connect that to the change object, every time our number changes, we will get a trigger. But as you can see now, every step, if it's turned on or off, doesn't matter, will produce a trigger. And to prevent that, we create a little gate object. Connect it there, and then we create an index object and give it the name of our buffer. And this will read the values written into our buffer. So it will close the gate when the step is turned off. And it will only pass through when the step value is turned on. Now we can connect that to our live.adsr object and also move over the live.scope object. And you can see we're getting some envelope shapes right here. Now I thought it would be cool to actually have two different options. One where the envelope is sustained for the whole length of the step, and one which is kind of a one-shot mode, so where the sustain is actually turned off and we just trigger the pure envelope shape. So we just create a selector object for both of these modes, connect a patch cord from the isn't equal to 0 object to the third inlet of the selector, and one after the change object to the second inlet. And then we insert a -subtract from 1 operator right there. And then connect the selector to the gate. And now we create a switch to toggle between these two modes with a live.text object. Add a +1 object connected to the first inlet of the selector device. And then we need to declare the loop mode for our live.adsr object. So it actually follows these two modes. And to get it right, we need to reverse subtract from 1 again. And connect all this to the live.adsr. And now we just rename our live.txt object to sustain. And now it actually should work as expected. Now let's hover over to the ADSR UI object. There you can declare some ranges for your attack and release values. I use it for visualization only, so I give it the ignore click argument. I disable the peak, final, and start handles, and I want to see the bounce of the object. And yeah, of course, you can declare all these values as you like them to be. That's just the way I would set them up, but that's totally up to you. And now we have a finished patch for Trance Gate Audio Effect. I skipped over some setup parts in this tutorial, like renaming all the live.dials and setting initial values and stuff, but I guess you can figure that out by yourself, and I don't want it to stretch out the video even more than it already is. And of course I made some little mistakes during this tutorial video, but we're gonna correct them now. So at first, the slope handles here, they actually have to be connected to the left outlet, of course, not to the right. As you can see, now they're working properly. The second thing is that this patch cord actually belongs to the reverse subtract from one object right here. Otherwise, our selector would switch it the other way around. And this patch cord right here actually belongs to the isn't equal to 0 object. Otherwise, our triggering algorithm wouldn't work as we want it to be. And now actually everything should work as expected. I also exported this whole patch as a little Max for Live device, which a little bit cleaner user interface and all that stuff. Ready to use, and you can download that, of course, from my Gumroad or my Patreon. And if you want to support my work so I can do further tutorials and more Max for Live devices, you can make a donation via my Gumroad shop or become a Patreon member. This really helps me doing all those patches and continuing my work. So this is very appreciated. And of course, if you have any further questions or other stuff, feel free to contact me via my socials or write a comment below the video, and I try to answer them as fast and as good as I can. So I guess I see you in the next tutorial, and now you of course get a little audio snippet on how this plugin actually sounds.